I'm Nuno. I'm a student at the Technical University of Lisbon, and I'll be presenting how we were able to build a JIT compiler for PHP in about, well, 2 or 3 days. This project started this year as a Google Summer of Code project that I was mentoring. The student is named Jonas Govenius. I hope I got his name right. And well, so let's see. So I'll start by presenting a brief overview of how the PHP VM works, some high-level description. The Zend VM is the official VM implementation for the PHP language, and then I will present how this really works, and also present some nice results, I hope. Okay, so how does the Zend VM work? So it is like a real simple piece of compiler technology. So it just performs some syntax-directed translation to bytecode, so it's really simple. There are no abstract trees involved nor anything, so it's just simple translation. Then it just interprets the bytecode, and it performs no optimization. So it just dumps bytecode and interprets it. Actually, now there is an extension that is being developed as we speak, and that aims to produce an optimizer for PHP bytecode, but it isn't ready just yet. Although there are some commercial extensions that do that. Okay, so how does this work? So we have the PHP script that gets compiled, then we have some bytecode that is outputted, and then we have this execute function that just interprets the bytecode. If we include some file, then we compile it and then execute it, and if there is some function call, well, we call this recursively. The interesting thing is that these execute and compile functions are actually hooks. So you can replace them with your own functions, which is what bytecode caches do. So what they do is that they replace the compile function, and then when they are asked to compile a file, they check the cache to see if the file has already been compiled before. If not, well, it just compiles normally. Okay, so now let's see how PHP bytecode is engineering. It is really different from what you see in other mainstream VMs. So it is memory-based as opposed with register-based like LLVM or Parrot, or stack-based like JVM or .NET stuff. So the PHP bytecode has references to specific memory locations, which is a bit weird, but that's how it looks like. Also, it has no standard representation. So there is no standard like textual representation, and there's also no standard way to serialize the bytecode to disk. So although there are some extensions that do that, there is no standard way to do it. Okay, so it is designed to be just executed and then throw away, and that's why it is memory-based. Because if it was like register-based, it would have to perform some register allocation pass. So this way, it's much simpler. The problem is that this poses some problems for our JIT compiler and for bytecode caches, because you can share a bytecode array between the processes, because it has references to specific memory locations. So each process has to have its own copy of the bytecode that is going to be executed. So here, this retrieve of cached opcodes is actually a really difficult operation. And finally, some information is not stored in bytecode. Why? Because PHP was engineering just to be executed and then throw everything out. So, for example, class definitions aren't stored in PHP bytecode. So they are set up in the VM when the file is compiled. So it's not like Java where everything is self-contained in the bytecode. This makes our life harder. Okay, so now let's see an example. So we have that simple script. I think it's easy to know what we will do. And here we have the dump of the bytecode. So we have that 1 greater than 2, which gets compiled to be smaller with the operand exchange, of course. And this is like a temporary variable. So don't be fooled. This isn't a register or anything like that. That's just a pointer to somewhere in the memory. Okay, so this is how the bytecode looks like. Okay, so now I'll try to explain you why we did the things the way we did. So our design is quite similar with what Apple did with the OpenGL shader JIT compiler. So, and I think the rationale is quite similar with them. So we didn't want to rewrite the whole VM from scratch because the VM is evolving every day, and our team is just me, so I can't keep with the pace of the development of the VM. So we clearly don't want to reinvent the wheel. So we want to reuse as much code as possible. Also, we were not completely sure that this was actually possible. So we really wanted to have some proof of concept really working pretty fast. And that's why the true or 3 days. So we wanted the proof of concept working. Also, we didn't want to constrain the future optimization. So we built it in a way that it allows future optimizations. All right, so how does this work? This is the important thing. So I would call this a speed-up plugin. So you don't change any single line of code of the actual VM. So you just load this as an extension to the VM. Okay. So it would be great if all programs had this kind of plugin. So in Vista, you would load like the speedup plugin and it will run really fast. But unfortunately, not all programs have this kind of speedup plugin. So yeah. Okay, so we hook in the bytecode executor as opposed with bytecode caches, which hook in the compiler. So we receive bytecodes as input, and then instead of interpreting them, we JIT compile it. Wait. Also, we update the state of the VM so that we can use the old interpreter or JIT. So, because for example, you may not want to JIT compile everything, because if you call like the eval function to eval some short piece of code, probably you don't want to compile it. Also, you may also want to JIT compile only hot pieces of code. So we allow that to be done. Okay, so how does this really work? So offline, when you install the extension, we compile the batcode handlers to LLVM bitcode and then optimize it. So every single batcode handler is compiled to a big LLVM file. This file is about 2 megabytes. So, and we then load this file at runtime. Okay, then we translate each bytecode to its Endler call, which you'll see. Okay, let me advance here. Okay, so let me advance to here. So we replace this function. Okay, so we receive the bytecode, and then we replace this function so that we can JIT compile things. Let me just, okay, I have here. Okay, so how the current executor looks like. So it is a very simple interpreter. So while true, do stuff. So what's in here? So this is the current bytecode that is being executed, and then we just call the handler that is capable of interpreting that specific bytecode. So this is just a function pointer which is cached for that specific bytecode. Then we look for the result because like 0 means go on, 1 means stop the VM, and so on. The thing is that most opcodes return 0. For example, add never stops the execution. So when we JIT compile and run the LLVM optimization, we can also remove that switch because we know that the handler always returns 0, for example. So JIT compiling also has the benefit that we remove a lot of code from being executed. Okay, so let's see an example. So let's try to compile this file to bitcode. So we have the smaller handler here. So let's compile it to bitcode. Okay, so what we do, we have this helper function, which is just a one-liner function, so that's a real problem. So, and then we call here the handler, which is going to execute that bytecode according to the parameters that are here, like the operands. These operands are in this structure. Then we do the switch that's here. We do this switch, but this will be removed by LLVM optimization because is smaller never returns this value. So this will be removed automatically by LLVM. Okay. So this is a compilation of this bytecode here. So is smaller gets translated to these 3 lines, which is kind of nice. Okay, a more difficult one is this jump, because jump updates the program counter. So we have to, that's a special case. So we use this Runtime Helper, which is also a one-liner. And then we have to switch and do this if to see to where we are going to jump. Okay. Now, the interesting part, the result. So if you see, vanilla is the current PHP implementation, and here is the best we can do, which is a nice performance. We get a slowdown. But let me first explain these results. So this here is the time to run a simple hello world program one time. So this time accounts for setting the JIT machinery, compile the function, optimize it, and so on. So this is not that bad. Why? Because in PHP, what we want is like to compile a script once and then serve like 1,000 HTTP clients with the same compiled program. So this is not that bad because the execution time is really small when compared with that. I don't have here the time to execute the function, but I forgot to put here. Okay, so now more realistic benchmarking. This is the standard Zend benchmark, which is used to keep track of differences between versions. And as you can see, the JIT performs worst in all cases. But there's a reason. So here we are not performing inlining. Why? Because last week when I did this, there was some regression in LLVM and the inliner crashes, so I had to disable it. So, but I haven't tracked the problem yet. But it was running like 2 years ago, 2 weeks ago. Yeah. So there was some regression last week, so I don't know what's going on. Anyway, this is not bad because this includes the time to compile and the time to optimize and the time to execute. So this is not really that bad. Also, I don't have the results for the time just to execute. So I apologize for that, but I don't really have the execution time. Also, I'm not showing here 3 tests, which I deleted them because with the JIT they never terminate. This is a problem somewhere that needs improvement in LLVM because the fetching of a function in JIT, I think it's too slow, and things like the Ackermann test, which is highly recursive, doesn't really play well with our implementation. So I've just chosen to hide that. But yeah, probably next week it will be fixed. Okay, so now the best part, which is like what we would like to do next month or so. So we would like to be able to share code between processes. So a typical PHP setup is like having multiple Apache processes, and we want to share code between the processes. So this will need like some code relocation, and I don't know. This is not that easy, but yeah, we want to eventually do this. Also, we want to be able to compile PHP code to native code offline and create self-executable apps, like normal apps and PHP GTK apps, Cocoa PHP apps, and so on. Although that's not entirely possible, because PHP is so dynamic that not all programs can be compiled offline, because you have like the include function that can receive some arbitrary argument, so you don't know which file will be included until runtime. So we want to do this, but only if the programmer uses only a subset of the the dynamic features. Okay, also another crazy idea is to have self-contained web apps for huge websites. So we want to compile like Apache and PHP and the PHP application to LLVM bitcode, and then perform all the link time optimization, and then you have a specialized web server just for your application. So I think huge websites that use PHP like Yahoo and so on will usually benefit from this approach. Okay, and optimization. So there is still there's still a lot of room for improvement for domain-specific optimizations that we can do. So while the LLVM optimizers are really great, they don't know the PHP language, so they can't do some like function lower, like strings reduction, for example. So they can't do all the optimizations. Okay, so I'm done for today, and I'll accept some questions. Okay, sure.
Notice that when you were doing the comparison between the two, it was actually a call down into the PHP library. Is that correct? So that seems like one of those obvious areas of optimization. Is that correct?
So here?
Yeah.
Okay, so
Zend is smaller.
see, okay, this is the handler from the Zend VM, but we compile this to PHP bitcode. So this gets inlined here. So this is not a problem. So this is the code that we emit, but then the optimizer will take care of that.
You actually are. It doesn't translate into a call into PHP's library. You are actually.
This is all inlined, then yeah.
Native instruction.
Yeah. And with that code removal, the code will be really small, because these handlers have a lot of ifs to know if the arguments are constant, if the argument is a number, if the argument is a string, and so on. But here we know the types of the argument. So this code will be really small. So. Okay.
I was just going to ask if the timings were with the inlining, or if they were the timings of this code.
Which one? Okay.
Yeah, these timings, were they just...
These timings are without the inlining,
okay,
because of the regression somewhere. But this is also the compilation time and the execution time. So I should have just the runtimes, but I didn't have time to do that. Okay.
Have you looked at the reasonably large PHP application? I mean, I have talked to Zend, and they said a major improvement they get in their acceleration, Zend acceleration, is through caching parsing. Basically, the phenomenon is that huge amount of code is developed, is there, but only a small fraction of that is executed. Now, if you think of that in the context of inlining, for example, it may not make sense to inline a huge code, which only a small portion of that is going to execute, because you're spending time doing things that are not going to execute at all.
Okay. The thing is that we inline, but we inline the Zend handlers. Currently we don't perform inline of PHP code itself. So if the user call a PHP function, a user level PHP function, that doesn't get inlined. The thing with bytecode caches in the PHP is that the parsing is very slow. So usually like half of the time of the execution is spent in parsing. Although the last version has a brand new parser made by me and a few guys. So I think now Zend doesn't have such strong arguments. So I hope they move to a JIT compiler soon. So yeah. Okay. Anyone else?
Okay. Well, thank you.
Okay. Thank you.